Hello, everybody. My name is Paul Cercueil. I'm a software engineer at Analog Devices, and today I'm going to talk about LibIIO and gr-iio. So I don't know if you noticed, but about 2 months ago, a new set of blocks were merged in GNU Radio, the gr-iio blocks, and I'm going to talk about this today. Um, First, I can't really talk about gr-iio without talking about IIO. So I'm going to do an overview of IIO. Then I'm going to talk about libIIO. Finally, I'm going to show the various blocks that you can use in gr-iio. I will end with a demo showing well how to use the blocks, and finally talk about the performance and future developments. So IIO stands for Industrial Input-Output Framework. It is a subsystem of the Linux kernel. It can be found in the kernel sources in driver/IIO. And it is basically for all the devices that don't fit in the hardware monitoring subsystem or the audio subsystem or the input subsystem. So in this IIO subsystem, you're going to find ADCs, stacks, VJs, PJs, magnetometers, gyrometers, and all kinds of sensors. It has wrappers to other subsystems. For instance, you can use a gyrometer, an IO driver for a gyrometer, and use it in the input subsystem. That totally works. It's widely supported by many vendors, including Analog Devices, of course, but also Texas Instruments, Xilinx, Qualcomm, STMicro, and many others. About the binary interface, so the IO subsystem has two main interfaces, the CCFS interface, which will contain all the metadata and allows you to set the parameters and configure really the radio. And then you have the dev interface, which you will have device nodes for each IO device, and it's used for streaming data from the IO device or to the IO device. Note that some devices only have the CCFS interface, the slow sensors, slow as in human scale slow, for instance, 10 samples per second or less. You don't really need to stream data. You can just read the data by polling an attribute. So these devices don't have a dev interface. For instance, to configure the gain control on ADALM-PLUTO from Analog Devices, you would have to go to sys plus IIO, then go to IO device 0, which is the device that allows you to configure lots of settings. In that folder, you will have the name, for instance, which is a device attribute, and then out voltage 0 hardware gain, which is the hardware gain for the first channel, and then out voltage 1 hardware gain, which is the hardware gain for the second channel, etc. So reading and writing samples. First of all, you need to enable the channel by writing the scan element / name of the channel underscore en, that stands for enable. After that, you just enable the buffer by writing the buffer / enable parameter. And finally, you just start reading or writing the corresponding dev node. There is a caveat to this, is that this is a slow interface because the data is copied between the kernel and user space. So to address this issue, Analog Devices developed a high-speed interface. It consists in a pool of buffers that are shared between the kernel and the user space. The kernel has two queues, one incoming queue, one outgoing queue, and it will endlessly going to pick one buffer from the incoming queue, fill it with the data coming from the DNA, then put it when it's filled to the outgoing queue. And then the application on the other side, on the user space, the application is going to dequeue the buffer of samples, read the data, process the data, do whatever it needs to do with the data, and then once it's done, just enqueues it back to the incoming queue of the kernel. And in this scheme, there is absolutely no copying of the data. The problems with this high-speed interface is it's specific to analog devices kernel. It is not upstream and it is not upstreamable. It was probably upstreamable when it came out in the early 2010s, but now it kind of there are no better mechanisms that could be used in the upstream kernel for this solution. The other thing is it is not as simple. It uses IOCTLs. You can't just read and write data using a bash script, for instance. I think it will eventually be deprecated and replaced by an upstream solution, as I said before, probably based on DMA buff, for those who know. Next, I'm going to talk about LibIIO. So LibIIO is the project I worked on when I first joined Analog Devices in 2014. As of today, there have been about 53 different contributors in the code. The goals of LibIIO is to provide an interface to the I/O subsystem and an easy-to-use one. Abstract away all the low-level details of the I/O framework, for instance, whether or not you're using the high-speed interface or if you're using the regular interface, your application shouldn't have to care about this. And it provides a high-level representation of I/O objects instead of having to deal with lots of file names with really strange structure. Then you have device object, channel objects, etc. On its design, it was designed to provide a very simple, easy-to-use API, and it's written in portable C99. It's modular, it's thread safe, and it runs on Linux, Windows, OS X, all the major operating systems. Inside LibIIO, you have different kinds of objects. You have first the top level object, which is the I/O context. The I/O context basically contains all the devices that you would find, for instance, on your target board. Your I/O context object can have attributes, which will be, for instance, the kernel version, the operating system, etc. Your context can have zero or many different I/O devices. Your device can have zero or many I/O channels, and your device can also have a buffer connected to it. And all these objects like device, buffer, channels can have attributes as well. As I said before, LibIIO is modular, so it has a clear separation between its high-level API and the backends. The applications using LibIIO are compiled against the high-level API, and so which backend you use is completely transparent to the application. So there are a couple of backends. For instance, there is the local backends to use the locally connected I/O devices. You can have a network backend, USB backend, UART backend, etc. And since your application is compiled with the high-level API, there is no distinction between backends. The API is the same, and as such, it can run with different backends. It doesn't even have to be recompiled; just works out of the box through USB or through network, etc. And this is a modular system because you can choose which backends you want compiled inside the library. You can compile only the local backend if you want to, only the network backend if you want to, or USB, or any combination of these. And the good thing with these backends is they allow LibIIO to be used on non-Linux systems. So you can use LibIIO remotely using the network backend or the USB backend on the Windows PC, for instance. And that's what makes it able to run on other operating systems. A small word about the applications that run on top of LibIIO. We have the I/O utils, which are shipped with LibIIO. I'm going to talk about them later. There is the I/O scope, which is used heavily internally at Analog Devices to debug hardware, and also by the clients, of course. There is the Scopy software, which is software oscilloscope and signal analysis toolkit that was designed for the M2K product from Analog Devices. And we have MATLAB, Simulink, GNU Radio running on top of LibIIO. And then third-party apps where Analog Devices didn't have any was not involved. for instance, SDR Angel, GQRX, SDR Sharp, etc. The context can be, since there are different backends, the context can be identified with the URI. URI is basically just the address of IEO context. For instance, you would have a USB colon 2.8.5, which identifies the IO context at the USB address 2.8.5, or you have IP colon IP address 192.168.2.1. These are examples of IO of URIs that are using LibIIO. A little bit about the command lines tools that are in LibIIO. IO info is the most useful one, gives you an overview of all the information that LibIIO has on the system, on the devices, on the channels, the attributes and their value, etc. IO at, which can be used to read and write IO attributes, IO read dev, IO write dev to read and write samples, and IO reg to read and write directly the registers. This is the output of IO info. I'm not going to talk that much about it. If you want to have a look after in the slide. LibIIO can be used, of course, in C because it was written in C, but also in C++ using the regular C API. And we also have official bindings for Python, C#, and MATLAB. There are also third-party bindings for JavaScript, for Rust, for Julia, for Lisp, Haskell, and probably others. That was just from a quick search on GitHub. Now let's talk about gr-iio. gr-iio basically is the gateway between IAO and GNU Radio. It was created a couple of years ago, I think in 2015. I created them in 2015. I was out of tree until about 2 months ago, where they were merged inside GNU Radio. In gr-iio, you have a couple of blocks. You have, for instance, the IO device source block, which is the block that allows you to receive samples from any IO device that supports the dev interface. And here, for instance, as you can see in the properties, we just set the URI, the device name that we want to read samples from, the channel, and then the data is going to flow through the output of the block. The IO device thing is basically the exact same. You just set the URI, the device name, the name of the channel, and you can upload samples to the IO device. Attribute blocks. So they allow you to read, write, and update attributes, be it device attributes or channel attributes. The IO attribute source just reads IO attribute at a given interval. The IO attribute sync just writes an attribute, and the IO attribute updater generates the messages at a given time interval to be used with the IO attribute sync. Then we have ADI specific blocks, the FMCOM2, 3, 4, FMCOMs5, and the Pluto SDR blocks. Source and sinks can be used with ADI specific products. These blocks are actually just specializations of the IO device source block. You can do everything you can do with a Pluto SDR source. You can do it as well with the IO device source and the IO attribute blocks. Now I'm going to present you with a demo, flow graph demo. I'm going to use the ADALM-PLUTO device from Analog Devices. It has a loopback cable between the TX and the RX. It's connected over USB to my laptop. And on the other side, I have a gaming handheld that is connected over USB as well. That runs Linux, and the joystick is connected to an IO device. So let's just start by creating a Pluto SDR source block because we want samples from the Pluto. So I'm going to do just this. We're going to configure it for 320 kilosamples per second, and with the given URI, USB 3.6.5. That's the address of my Pluto. I'm not going to leave the other settings to the default because I don't know what most of them do anyway. And we're going to leave the base frequency at 2.5 gigahertz. That's fine. And I'm just going to enable a time plot and a frequency plot so that we can see what we are receiving. As you can see, that's not very interesting. We're just receiving zeros. There's nothing going on. So let's actually actively send something on the TX so that we can loop it back to the receiver. I'm going to enable Pluto SDR sync that's configured for the same URI, same settings, same sample rate. I'm going to send it a 10 kilohertz sine wave. Yeah, I'm just going to send a 10 kilohertz sine wave. And I'm going to enable this block, which is a Qt range. That's a widget that I'm going to use to change the attenuation. So let's start. As you can see now, we have a beautiful sine wave. That's what we send on the emitter and receive on the RX side. And if I change the attenuation on the transmitter, as you can see, higher attenuation means lower amplitude, smaller attenuation means higher amplitude, just as you would expect. That's still quite a boring demo. What we can do something more interesting. Because right now I'm using Pluto, which is a product from Analog Devices, and I'm using the Pluto sync and the Pluto source. That's not very generic. That's still very specific to Analog Devices. But what I can tell you is that this Pluto sync, for instance, we don't really need to use it. We could very well use a regular IO device sync. So I'm going to do just this right now. So I'm going to disable the Pluto SDR sync. We're going to enable the IO device, the regular IO device sync block. So it's configured the same way, same URI, USB 3.6.5. That's the address for my Pluto. We're going to use the CF AD9361 DDS core LPC, which is the device name where we can stream the data with the channels voltage 0, voltage 1. And what we have in the middle is just to make sure that the data is properly scaled to the maximum range of the DAC. There we go. Let's try again. And as you can see, we have more or less the same sine wave. What is not going to work, however, is the attenuation slider, because this was just setting a property in the Pluto SDR sync. And now we don't have the Pluto SDR sync anymore. However, we can still make that attenuation slider work using the IO attribute updater and the IO attribute sync blocks. The IO attribute updater, what it is going to do is just send messages key equals value every given time. So now we just configure it for a 500 millisecond interval, and every 500 milliseconds is going to send hardware gain with the value that is set in the range. However, since we are setting hardware gain and not an attenuation, then the value needs to be negated. So this block just negates the widget value. Then the IO attribute sync will just say that the messages that we receive have to be returned to the AD9361 PHY block. Sorry, AD9361 PHY device to the output channel voltage 0. And now if we start again, we get the same sine wave, and as you can see, if I decrease the attenuation, then we increase the amplitude. If I increase the attenuation, then it reduces the amplitude, just like before. So now we're going to do something a bit more interesting. I'm going to disable all of this. We're going to receive data, like raw data from the joystick that is on the handheld. So I'm going to enable the IO device source block, which is properly configured with the address of my handheld. We're going to use the JZ-ADC device, JZ-ADC device, which is the device that delivers the data, and using the voltage 3, voltage 4 channels. And just so that you can see, I'm just going to print them on the time sync, on the time plot. We have to scale the data. We're going to scale the data to 0 up to 2 range so that it can be displayed properly. And the sample rate of this data is more or less 35 samples per second. It's pretty slow. So I press play now. We still have our previous data that is now pretty not interesting. This is the joystick output. As you can see, if I press up on the joystick, then my y-axis moves. If I press down, it moves the other way. And then if I move the x-axis, then the x-axis line moves. So the reason I scale this in the 0 and 2 range is because we're going to shape a signal that we're going to send on the sync. We are going to have 2 sine waves, one which is 10 kilohertz and one which is 1 kilohertz. And we're going to multiply these 2 sine waves with the value of the axis that we get. So to be able to do this, knowing that we have on one side the Pluto SDR sync, Pluto SDR source, which work at 320 kilosamples per second, and on the other side the IO device source, which works at 35 samples per second, we need to a repeater block in the middle. So this block is going to repeat the samples from the joystick so that the 2 sample rates more or less match. Then we're going to scale the data so that we get in the correct range, convert them to complex, multiply them with the sine waves, just add the 2 and send them to the sync. And I'm going to keep this enabled because it's interesting to see. Yeah. And I think that's all. Let's execute the flow graph. And now you can see in the middle, we have the sine wave that we're receiving. It's quite small. I'm going to lower the attenuation a little bit. Yeah, they should be fine. And now, as you can see, if I raise the y-axis, so raise the joystick, the 10 kilohertz sine wave increased in amplitude. The value is in dB is much higher. And if I lower it, then it looks like we almost only have the 1 kilohertz sine wave. Then if I move the X joystick, you can see on one side I can really reduce the 1 kilohertz sine wave, and on the other side I can just make it more strong. So this is an example of how you can use the gr-iio blocks with a real SDR focused hardware, which is the Pluto, but also with something that was really not sought for SDR, which is just a regular joystick on a gaming handheld. Yeah, that's my demo. A little bit about LibIIO performance now and GRiO performance. On the right side, you can see the local backend performance. if you have buffers big enough, so 8K samples or more, then you can go as high as 60, 70 megasamples per second, not lose any data. If you have smaller buffers, then you might actually start to get underflows, overflows. On the IP backend, the USB backend, it's a different story. There, the buffer size really changes the sample rate that you can reach without losing data. Using a small buffer, for instance, 1K samples, then you're going to start losing data at 2 megasamples per second. If you use a bigger buffer, 16K samples, 32K, 64K samples, then you can reach maybe 8 megasamples per second, 10 maximum, without losing data. And above this, you're going to lose data. The problem is that the communication between LibIIO and the IIO daemon, which is the server side of LibIIO, is synchronous. You just ask for data, the server sends data, you ask again, the server sends again, etc. So if you have big buffers, that means you spend more time transferring data and less time asking for data. And if you have small buffers, then you basically just spend your time asking for new buffers. So there is really room for improvement using an asynchronous protocol, using a better mechanism inside the IO daemon based on DMA buff, as I talked before, so that there is no data copy within IOD itself. And so far we've had promising results with current experiments. It went from 24 megabytes per second peak to maybe 82 megabytes per second on the network backend with the Pluto. And that's my presentation. Thanks a lot for following. And if you have any questions, I will be glad to answer them.